Jai Hind, myself Richa from Department of Electronics and Communication, Ajay Kumar Garg Engineering College. Today we will discuss about the magnetron. Magnetron is basically a microwave source. So this is the division of microwave tube. Microwave source tubes are nothing, these are microwave source, right? So tubes are microwave source. In electronics, vacuum tubes are also available, but we cannot use vacuum tubes at microwave frequency. There are some limitations of vacuum tubes, so that we cannot use vacuum tubes at microwave frequency. So we go for the microwave tubes. So microwave tubes can be divided into two parts. First is the ordinary type of microwave tube, and second is the magnetic type of microwave tube. So ordinary type of microwave tube is basically called a linear beam tubes, or it is sometimes called O-type tubes. So O-type tubes, in this the beams of signals which are generated in the linear form, and here it is again divided into three parts. One is the klystron tube, traveling wave tube, and klystrons, right? So this klystrons is your microwave source which is used to generate microwave signals, and traveling wave tube is also a microwave source, and this is again a microwave source. It is further divided into four parts. One is the helix tube, backward wave oscillator, couple cavity, ring bar, or it can also called ring loop, right? And the klystron is divided like a two cavity klystron, multi cavity klystron amplifier, and the reflex klystron. In the reflex klystron there is one cavity present, and from this cavity only microwave signals are generated. In two cavity klystron, two cavities are present. One is your buncher cavity and another is the catcher cavity. In the multi cavity klystron there is a combination of two cavity klystron, so there is a bunch of cavities are present here. So signal will be amplified by two cavity klystron. After that again one cavity will be present, it will again amplify. So this is these two are used for amplification of your input signal, or we can say we are providing some input signal which is amplified by these two type, and the amplified signal is the microwave signal. So today we will discuss about cross field tube, which is called magnetic type of tubes, or sometime it is called M type tubes. It is divided into magnetron, cross field amplifier, and cyclotrons. Okay, so today our lecture is based on the working and construction of magnetron. So what is cross field basically? So a magnetron is a device that generates high power electromagnetic waves, and it is basically considered as a self excited microwave oscillator, and it is known as a cross field device. Why it is called as a cross field device? As the electric and magnetic field which is produced inside the magnetron are perpendicular to each other. So because of this because of this electric and magnetic field perpendicular to each other, it is called cross field tubes. So first we will discuss different type of magnetron. Basically there are three type of magnetron. First is called negative resistance magnetron, right? So in this type of magnetron, it will use negative resistance between anode segments, and but have low efficiency, and it is useful only at the low frequency. So the negative resistance between anode and cathode will be used to generate a microwave signal, but the efficiency of this type of magnetron is very low, and it is able to generate a low frequency signal. So if we want to generate a low microwave frequency signal, so we will use negative resistance magnetron. Second type is the cyclotron frequency magnetron. In this, it depends on the synchronization between the alternating component of electric and magnetic field oscillation of electron in a direction parallel to the field. So the we can say that the oscillation of electric and magnetic field of electrons will be responsible for the generation of the signal, and this type of magnetron can be used to generate a signal more than 100 megahertz. It means less than 100 megahertz signals can be generated by negative resistance magnetron. Third one is the cavity magnetron. It depends on the interaction of electron with the rotating electron magnetic fields of constant angular velocity. Okay, so it provides oscillation of a very high peak power and hence are very useful in the radar applications. So these are the three types of magnetrons. So operating principle of magnetron, it is basically a vacuum tube of high power having multiple cavities. There is one center cathode and number of anodes are around situated in a circular fashion across the cathode. It is also known as a cavity magnetron because of the presence of anode in the resonant cavity of the tube. The operating principle of magnetron is such that when the electron interact with the electric and magnetic field in the cavity, then high power oscillations get generated. So because of the interaction of electron with the electric and magnetic field, your microwave signals are generated. These high oscillation signals are called microwave signals here. So this is the construction of magnetron. See here, it is cut from one side and this is the inner view of the magnetron. So this is the cathode, the center. Here in the center we have used one cathode and these places we have put anodes, right? So these are the anodes. Okay, so in the circular fashion, in the center there is a cathode and the circular anodes are connected across its circumference, right? And here RF output is taken out. This is the point where it means one of the anode, from the one of the anode we are taking the output. So output is taken from anode, right? And here we are providing DC field to the cathode, so there will be generation of electric and magnetic fields. So this is the construction of magnetron. So in the last figure it was 8 cavity magnetron. 8 cavity means the anodes here present are 8, number of anodes are 8. A cylindrical magnetron has a cylindrical cathode at a center at a certain length and radius present at the center around which a cylindrical anode is present, right? And the cavities are present at the circumference of anode at each spacing. Also the area existing between anode and cathode of tube is known as the interaction space region. So this area, basically the area between anode and cathode is the interaction space. So electron will interact in this space only. So there exists a phase difference of 180 degree between adjacent cavity. So if there are 8 cavities are present, so the phase difference between these cavities should be, adjacent cavity should be 180 degree. So therefore cavity will transfer their excitation from one cavity to another with a phase shift of 180 degree. So working of magnetron, the excitation of cathode of magnetron is provided by a DC supply which cause the emergence of electron from it. See here. So this DC supply is responsible for generation of electron. So these electrons are generated from this DC supply. So there are two cases. One case when RF input is not present. Second case when RF input is present. So first we will discuss when there is no RF input is present. It means we are not giving any external RF signal to amplify it. So when RF input is not present, so there will be 4 cases. Case number 1, when magnetic field is 0 or absent, right? If there is no magnetic field, so what will happen? When the magnetic field is absent, then the electron emerging from the cathode readily moves toward the anode. It means it will go straightway from cathode to anode. The path of your electron is not affected by any field because RF input you are not giving and there is an absence of magnetic field. So, in between the interaction space, basically the magnetic field is present. Okay, and if we are not giving any RF input signal, so magnetic field is 0. If the RF input is not given and the magnetic field both are 0, right. So, if I am drawing it here, if this is your magnetron, in the center, if this is cathode and there is number of anodes here, right, and if I am saying that electrons are emerging from cathode, and if magnetic field is not present, magnetic field is 0, right. If this magnetic field is 0, so what will happen? This electron will start moving and it will go to anode. So, there is a direct path between, straight path between your cathode and anode. So, this is so because the moving electron does not experience the effect of magnetic field and moves in a straight path, right. So, see here, resonant cavity magnetron, high power, high frequency oscillation. This is the top view of your magnetron. So, this is the construction of the magnetron and these are the resonant cavity, or we can say all these are the anodes present here, and at the center we are using leads to cathode or heater because at the center we are using cathode and from this cathode electrons are emitted, right, and these are the copper blocks. So, see, whenever electrons are injected from the cathode, right. So, these are the from here the electrons are injected and these are the cavity 1, or you can say these are the anodes present here, 8 cavity, 8 anodes. So, electron has to move this, and this between in this is the interaction space, right. So, this is the interaction space. It means electron will interact with in this space. So, electron will interact with the magnetic field or electron will interact any RF input which is applied here only in this space only. If your electron is interacted with some field, then the direction or speed of the electron is going to change. At here I am denoting A, B, C, D, right. In the further slide we will define what is the meaning of A, B and C. So, A is the time when your magnetic field is 0 and you are not providing any RF input. So, electron emitted from cathode will go straight to the anode. So, case 2, when small magnetic field is present. Now, in between this space some magnetic field is present. So, what will happen? If there is a presence of some magnetic field, so what will happen? In case a small magnetic field existing inside the magnetron, the electron emerging from the cathode will slightly deviate from its straight path. See here the case of B. At time B, there is some presence of some magnetic field. So, the path of your electron will divert from the original path, and this deviation is because of the external magnetic field, right, and this will cause a curve motion of electron from cathode to anode. See here, now electron will move with a curved path. So, this curving will depends on the magnetic field, how much magnetic field is present between these two. So, this motion of electron is the result of action of electric as well as the magnetic force over it. Case 3, in case when the magnetic field is further increased, it means the magnetic field between this interaction space is again we have increased, and the electron emerging from the cathode gets highly deflected by the magnetic field and it goes along the surface of the cathode. See here the case C. So much magnetic field we are giving that this electron C will move across this path and come back to the cathode, right. So this causes the anode current to be 0. The value of magnetic field that cause anode current to become 0 is known as a critical magnetic field. So at the point C, the critical magnetic field is that when the electron will not reach at the anode. So anode current is 0. So if we again further increase the magnetic field, or we can say if the magnetic field is increased beyond the critical magnetic field. So critical magnetic field is the field when electron C is gazing across its circumference, right. So the electron will bounce. If we are further increase the magnetic field, then electron will bounce back to the cathode itself without reaching the anode. See here the case of D. Now magnetic field is further increased and electron will bounce back to the cathode. It will never reach to the anode. So the reaching of emitted electron from cathode back to it is known as the backheating. This is basically the backheating, right. So to avoid the electric supply provided to cathode must be cut off after oscillation have been set up in the tube. So when oscillation gets start up, we must switch off the cathode supply. If we are again giving the cathode supply, then this type of backheating will be coming into the magnetron, which will heat up your magnetron. So the second case, when the RF field is present. From the last 3-4 slides we have discussed that external RF field is not given. Now we are providing an external RF field. So what will happen? Case number 1, in case an active RF input is provided to anode of the magnetron, then oscillations are set up in the interaction space of the magnetron. It means now we are giving a RF input to your anode. So oscillation will be formed in the interaction space. When an electron is emitted from the cathode to anode, then it transfers its energy in order to oscillate. So it means the electron which is coming out from the cathode, now it will interact with the oscillation which are produced by the RF input signal from the anode, and because of its interaction, the electron will transfer its energy to the interaction space and it will move to the anode. Such electrons are called favored electron, right. In this condition, the electron will have a low velocity and thus will take a considerably high amount of time to reach from cathode to anode. If I will draw a diagram of this magnetron like this, these are the cavity. I am drawing only half diagram, right. So this is your cathode and these are the anodes, and we are saying that we are giving some RF input to the cavity. So there is a oscillation will be produced here. So these type of oscillation will be formed in the cavities magnetron, right. Now one electron A is starting from here, right. So A will take its energy and it will take longer path to reach to anode, right. So this is the favored electron. It means we require this type of electron which will give its energy to the interaction space, and this energy we will catch up as a output signal. So another condition arises in the presence of this external RF field. In this case, emitted electron from the cathode while traveling takes energy from the oscillation, thereby resulting increase its velocity. Now this type of case will also happen that the electron can take energy from the oscillation. If it will take energy from the oscillation, then speed of the or velocity of the electron gets increased, and because of the high velocity of the electron, it will take lesser time and move to the anode. So despite reaching the anode, the electron will bounce back to the cathode, and these electrons are known as unfavored electron. So in case if I will draw again, so this is the cathode and there are number of anodes present here, right? And we are saying that RF input signal is applied. So there is oscillations are formed. Now one electron is emitted from cathode. I am saying B. Now this electron while delivering energy to the interaction space, it will take energy. So if it will take energy, then it will take energy from the oscillation, and velocity will be increased and it will come back to the cathode. So this type of electron we do not require, because this will take energy from the interaction space and overall energy of the system is going to decrease, and these type of electrons are called unfavored electron, right? When the RF input is further increased, then electron emitted while traveling increase its velocity in order to catch up the electron emitted earlier with comparatively lower velocity, right? So all those electrons that do not take energy from the oscillations for their movement are known as the favored electron, and these favored electron from electron bunch or electron cloud and reach anode from the cathode. So the formation of electron bunch inside the tube is known as the phase Foxing effect. So due to this, the orbit of electron get confined into spokes. See here, orbit of electrons get confined to its spokes, and these spokes rotate according to some fractional value of electron emitted by the cathode until it reaches anode while delivering their energy to the oscillation. So the movement of this favored electron inside the tube enhance the field existing between the gap in the cavity. So these favored electrons will enhance the field between the gaps in the cavity. This leads to sustained oscillation inside the magnetron, thereby providing high microwave signals. So this is the anode and cathode, this is the electron path. Okay, so in this way signals can be generated from the magnetron. So there are two terms, one is the frequency pushing and one is the frequency pulling. So variation in the oscillating frequency of the magnetron give rise to the term frequency pushing and pulling. So the variation of this, what is that oscillating frequency? Oscillating frequency is because of the oscillation of the electron-electric field and magnetic field. So when the voltage applied at the anode of the magnetron is varied, then this causes the variation in the velocity of the electron moving from cathode to anode. This resultant changes the frequency of the oscillation. So it means first change of the oscillation of the frequency is because of the external applied voltage at the anode. So because of this, oscillations are formed in the interaction space, and when electron interact with this interaction space, then the oscillation of electrons are going to change. So this change in the frequency of the oscillation. Therefore, we can say when the resonant frequency of the magnetron shows variation due to change in the anode voltage, then it is known as the frequency pushing. Why pushing? Because we are giving some external supply, and from this external supply oscillations are going to change. It means external factor will affect the change in the frequency of oscillation, right? Next, the change in resonant frequency is sometimes a result of the change in the load impedance of the magnetron. If this change is because of the load impedance of the magnetron, the load impedance varies when change is purely resistive or reactive. If it is pure resistive, then it is going to change. If it is pure inductive or capacitive, we can say reactive, then also it is going to change. This frequency variation is known as the frequency pulling. Steady power supply can provide a reduction in this frequency variation. So one hull cutoff voltage is here after if we are giving field to the cathode, and this is your magnetic field. After that, if we are increasing the magnetic field, then your electron will come back to the cathode and back heating will be created. So the equation of motion for electron in a cylindrical magnetron can be written as d square r upon dt square minus r d phi by dt square is equal to E by m er minus E by m r bz d phi by dt. M is the mass of the electron, E is the electron charge. So this equation can be rewrite 1 upon r d by dt r square d phi by dt is equal to Em bz dr by dt. So B naught is equal to bz, B naught is equal to bz, and it is assumed in the positive z direction. It means rotation movement of your electron is in the positive z direction. Rearrangement of the above equation result in the following form: d by dt r d phi by dt is equal to E by m bz r dr by dt is equal to 1 by 2 omega c d by dt of r square. So when your omega c is equal to E by m bz, this is called cyclotron angular frequency, right? And on integrating the last equation, r square d phi by dt is equal to 1 by 2 omega c r square plus some constant at r is equal to a, whereas a is the radius of the cathode cylinder. So d phi by dt is equal to 0. So constant is equal to 1 by 2 omega c a square, because this dy by dt is 0 at r is equal to a. So constant will comes minus of, it means see here it comes out to be 0 is equal to 1 by 2 omega c r square plus some constant. So c comes out to be minus 1 by 2 omega c r square, right? So the angular velocity can be written d phi by dt. It means in place of this constant we will write the value of c, and after rearrangement of the equation it comes out to be 1 by 2 omega c 1 minus a square by r square. Since the magnetic field does not work on the electron, the kinetic energy of the electron is given by 1 by 2 mv square is equal to E into V. E is the charge and V is the field applied across this cathode. So at r is equal to b, next case when r is equal to b, where b is the radius from the center of the cathode to the edge of the anode. See here, if I am drawing a circular magnetron, so this is your cathode, right, C, and the radius of cathode is a, and now radius of this complete structure is b. So case when r is equal to b, right? So voltage V is equal to V naught, dr by dt is equal to 0 when your electron just gaze the anode. It means the case when it is moving just like this. C, d phi by dt is equal to 1 by 2 omega c 1 minus a square by b square, and it can rewrite b square is equal to d phi by dt square is equal to 2 em v naught. So substitution of b square in d phi by dt. So B square 1 upon 2 omega c. So in this equation we will write this value. B square 1 by 2 omega c 1 minus a square b square, the square root is equal to 2 e m by v naught. So electron will acquire a tangential as well as a radial velocity. Whether the electron will just gaze the anode and return towards the cathode depends on the relative magnitude of V naught and B naught. B naught is your external magnetic field which is applied. So the Hull magnetic equation is obtained 8 V naught m by E 1 by 2 B 1 minus A square by B. It means if your external magnetic field is greater than cutoff magnetic field for a given V naught, the electron will not reach the anode, right? So this is your condition for sustained oscillation in the magnetron. Cyclotron angular frequency. Since the magnetic field is normal to the motion of electron that travel in a cycloidal path, the outward force is equal to pulling force and it is given at mv square upon r is equal to evp, where r is the radius of this path and v is the velocity of the electron. So this angular velocity of circular motion of the electron is given as omega c is equal to v by r, which is equal to eb by m. V is the velocity of electron and r is the radial path which is followed by the electron, E is the charge of electron, B is the external magnetic field and m is the mass of electron. So these are some advantage and disadvantage of magnetron. Magnetrons are a highly efficient device which is used for generation of high power microwave signals. It means in all the type of microwave source, this is highly efficient and it is basically used for high power microwave signals. The use of magnetron in radar can produce radar system of better quality for tracking purpose. The main application of this is magnetron is in the radar and it is usually small in size than less bulky. We can see the magnetron is of very small size, circular, very small, physical size of this magnetron is very small. Disadvantage, it is quite expensive. Despite producing a wide range of frequency, there exists a drawback in controllability of generated frequency. It means high frequency generated, but there is an issue of controlling of this high microwave signal control. It offers average power of around 1 to 2 kilowatt, right? Magnetrons are quite noisy. It means this electronic noise is generated very much large from this type of source. So these are some applications of microwave magnetron. A major application of magnetron is present in pulse radar system and in order to produce high power microwave signals, because it is a source of high power microwave signals and it is used in the pulse radar. Magnetron are also used in heating appliances like microwave ovens so as to produce fixed frequency oscillations. Tunable microwave magnetron find their application in sweep oscillation. So main application of magnetron is in the radar system and in because the magnetron can be used to generate low power also. So this low power magnetron can be used for heating purpose and heating appliances like a microwave, and tunable magnetron can be used in the sweep oscillator. Thank you.